Before we start the continuation of chapter 16, I want to talk about the quiz. I saw, as you may have seen in your graded quiz, and I tried to grade it as quickly as possible so you can see what you have done. There were mistakes almost in everybody's solution. And I was surprised with that because usually the work energy problems are the easier problems of the dynamics course. Is a single equation, as you see. Sometimes you may have to incorporate kinematics, or when you calculate the velocity from half mv squared, they ask you to find normal forces. You have to go to normal tangential coordinate system to find that, which we did some examples of that. But if none of them is involved, practically you have a single line of equation, 3-4 terms, and you need to implement the concept and put the numbers. And I saw almost everybody made some mistakes. Now I'm going to explain how the problem is done. I usually do not solve midterm quiz problems because you already have done it, and if I grade it, you get the feedback. But when almost everybody makes some mistakes, I think we may need to add just some of the stuff. So this is your quiz, right? You had a vertical rod. You had this mass at the stationary at this position, H above the spring. You have the numbers. H is 500 millimeter. The mass is 2 kilogram. And the stiffness of the spring is 100 Newton per meter. So the problem asks the first part, how much is the velocity when the formation of a spring is 0.1 meter? Practically, if this is position 1, your position 2 would be somewhere like here. The deformation, I don't know, some of you use X, I usually use delta, let's just use X. X1 or X2, technically this is 1, is 0.1 meter. Right? So you go from position 1 to position 2. If you write T1 plus V1 equals T2 plus V2, most of you neglected the fact that after the collar touches the spring, it goes down a further distance of X2. So technically, if you consider your T1 is 0, V1, and let's set my reference here. I'm going to set my reference here as Y. So it's going to be mgh. T2 is going to be half mv2 square, and V2 is going to be minus mg x1. Why? Because you are this much. Sorry, this should be your reference. If this is the reference for Y, from here to here is 500. And from here to here, you go down by X2. And because it's below the reference level is negative, and also you have half K X2 squared. So you put this thing together, you find your V2, right? I'm not going to get the numbers. You can do it later. But many of you have missed this term. Unless we say it's negligible, you don't miss dimensions, velocities, masses, anything, right? And usually if something is negligible, we say, now 0.1 meter or 100 millimeter compared to 500 is 20% is not negligible, right? So you need to consider that. Any question about this? Now, if we do the second part, part B, as for maximum deformation of a spring. And I have seen some of you have done completely, like maybe 2-3 students, completely irrelevant stuff. That means you haven't got the concepts as deep as you should. So please go and review stuff. But when it goes to the bottom, the lowest place for the maximum deformation, usually maximum deformation in spring, what happens? It goes down completely, it stops for a moment and bounces back up usually, right? That moment that goes down with maximum deformation, how much is the velocity of that object? Callie, if it goes down all the way, how much is the velocity?
I'm not sure.
I just explained it kind of implicitly. I said it goes down all the way, it stops momentarily, right? And then goes back. Is this correct? So if it goes all the way down to the maximum deformation and temporarily stops, that the stop means the velocity is 0, right? All of the kinetic energy and potential energy of gravity is used to create deformation in a spring. I don't know if you see my hands. It goes down all the way here, it stops for a moment and goes back. So the lowest place that the particle goes for the maximum deformation, velocity is 0. Now, if that's the case, you can use 0.2 as your starting point, or you can use 0.1 as your starting point. Okay. And consider it like a new problem. So if I consider 0.1 here for the case B, so this is position 1. Position 2 is when it goes all the way down somewhere here, right? And it stops. So you're going to have the formation of X, let's call it X3, because this is the case, another case. It goes from 1 to 3. So from 1 to 3, you still have conservation of energy because there's nothing else. It's exactly the same as before. T1 plus V1 equals T3 plus V3, and everything is the same. T1 is 0 because problem says it starts from rest. This time T3 is 0 because of the maximum deformation means V3 should be 0, right? And again, if I keep this level as reference for Y, V1 is going to be mgh, same as what we had. V2 is going to be mg. Now this is x3, the amount of distance that this object, this mass goes below the reference Y is x3. So you're going to get minus mg x3 plus half k x3 squared. And if you put them in the equation, you're going to get mg h minus mg x3, sorry, equals minus mg x3 plus half k x3 squared. This is a quadratic equation. You can simply put everything on one side. Half k x3 squared minus mg x3 minus mg h equals 0. This possibly gives you 2 solutions, right? This gives you 2 solutions. One x3 is usually negative and one x3 is positive. Remember, x3 we already consider going down, so its value should be positive. So you take the positive number, right? and then you solve it just like that. So you take a positive number, and that's your x3. Many of you, not many, like maybe 2, 3 miss these things completely and put, for example, x, like f equals x, I don't know, 3, and then x3 is like f over k, and this is completely irrelevant because this is not static. This is not the only force acting here, so you shouldn't do that. Now, this is how, and I think the concept was not as complicated, right? Something you guys missed, quite few of you, is that when you go below the level, this has to appear in gravitational potential energy, right? And if you do that, you get it done. Any question about this? And with all explanation, of course, you're going to have to calculate this. It took almost 10 minutes to do this. So it wasn't very time-consuming problem, right? Okay. So please remember these concepts that we had here, quadratic equation. And if you get something similar, anytime you get the maximum deformation of a spring, that means the object pushing the spring or pulling the string reaches 0 velocity. Possibly after that it's going to bounce back, but we're not talking about the next step, right? The problem asks at this moment, find it. So you go from 1 to 3. Okay. Good. Now let's go back to the slides. We talked about general motion, rotation, translation, all of that for rigid bodies, right? We talked about the concept of rigid body. Excuse me. Now, the first type of motion we analyze in this chapter, which likely is the simplest one, is translation only, or as I call, you know what, let's just remove this word pure because I think pure is not a good number. We have to fix things one day, right? Translation of rigid bodies. Now, to analyze translation of rigid bodies, we go to relative motion analysis. I want you guys to pay attention to this simple animation. Imagine this is your rigid body, something with whatever shape, right? And it translates without rotating. So this is translation, right? Goes from this point to this point, no rotation of any kind. Now, if we consider relative motion analysis, remember in chapter 12, we talk about relative motion analysis between 2 points, right? Or 2 particles, which is mathematically 2 points. I'm going to pick those 2 points, A and B, on this same rigid body. I can do that, right? You can write the relative motion between any 2 points in the universe. I pick the 2 points on the same rigid body. And if I do that, technically, the vector position of B is the vector position of A plus position of B respect to A in this moving coordinate system, which is like this guy, RB respect to A, right? So if you write that, we're going to get RB is RA plus RB respect to A. Any question about this? Or you guys don't remember this from chapter 12? Chapter 12 was like long time ago, like 3 weeks ago. Right, Kelly? It's too far to remember. Okay. Excuse me. So, but hopefully you remember from the basic math that you have three vectors. RB is the summation of RA and RB respect to A. So RB is the absolute vector showing the position of B. RA is the vector that shows the absolute position of A with respect to this fixed XY coordinate system. RB respect to A is how A sees B in this moving coordinate system. Now, if I want to find velocity, what do? I take the time derivative of this, right? So the time derivative of this RB is going to be VB, RA is going to be VA, but how about this guy? The time derivative of RB respect to A. Practically, it should be the velocity of B respect to A. But there are two things to consider. First, A and B are on the same rigid body. What that means? You remember the definition of rigid body? The distance between 2 points on the rigid body remains the same, right? So technically, because A and B are on the same rigid body, the length of RAB or RBA doesn't change. The second point is, for a vector to change, either the magnitude or the direction should change, right? Does the direction of RB respect to A, this vector, change? And I want someone to tell me yes or no. You know what? Let's take a vote. Those who say yes, raise your hand that the direction of vector BA changes. Those who say no, raise your hand. Half of you have no idea, huh? No opinion. This is not like a political voting. You have to say yes or no. You can go neutral. Okay. Remember, this is translation, right? Translation means no change of angle, which means this vector remains same direction, same angle, which means it is a constant vector. If RB respect to A is constant, then its derivative will be 0. So if that's 0, technically VB is equal to VA. So when it's about translation, and we chose A and B kind of randomly, right? So it means any point on this object has the same velocity. You take the second derivative, you realize that any point on this rigid body has the same acceleration. So practically, when you have a rigid body with translation, it's like a particle. Everything moves together. You can choose one point, analyze that, and everything else is the same. Does that make sense? Maybe now you realize why in chapter 12 we chose some of the big objects as particle. Because if you neglect the rotation part, every point has the same behavior, right? So you pick one of them, goes the same. Any question? So this is for translation. When we talk about rotation, and let's just take the pure away here too. So for the rotation, look at this object that rotates about an axis. So, oops, sorry. I don't know if you guys have ever had shawarma or doner kebab like this, Middle Eastern sandwich. You don't know what it is, right? Andrew, you know what it is, right? How they make it, they have a long, like a, almost is like a, I don't know, like a stick, let's call it a stick, and then put the layers of meat on top of each other, and then it rotates, and one side is heat flame or elements or fire and rotates slowly and it cooks the surface part of the meat, then they take the slice of the cooked part, create the sandwich, and as they go, it just keeps rotating and rotating and they take it, things like that, okay? Anytime I teach this course, this reminds me that because it's exactly the same thing. You can have just layers of chicken breast or I don't know, beef or whatever it looks like that. That is something that has pure rotation about a fixed axis, right? Doesn't move around. Now to analyze this, we need to see for rotation, remember, rotation is about the change of an angle, right? That's how we define rotation. A line in the rigid body will change its direction and then changes its angle. So to measure the angle, we need a reference line. Suppose that the point P is here, as the original angular position is theta. If this rotates and goes to point P prime, then it's going to have an angular displacement of d theta, delta theta. Anything we had for linear displacement, s, delta s, v, acceleration, we're going to define it for angular position, displacement, velocity, acceleration, okay? So, first of all, angular and position and displacements are not vector, right? Do you know why? Because vectors follow certain basic mathematical rule. So angular velocity comes with the change of angular displacement over time, and angular acceleration comes with the change of angular velocity over time. So practically, whatever you had for S, V, and A, now we have for theta, omega, and alpha. So we show the angular velocity by Greek letter omega. This is not W. Some of students use the word W. Is it omega? And we use the Greek letter alpha for angular acceleration. So the change of angular position is velocity. The change of angular velocity is acceleration. And if you want to find instantaneous velocity and acceleration, that delta turns to differential d omega dt, or here, d theta over dt. Okay? And I'm sure you remember this from your physics. You had these things in your physics, mechanic physics, right? Physics 1. Do you guys remember that? I think only Callie remembers. I don't see the others say yes, so. Okay. And if we eliminate time between the two equations, you're going to get omega d omega alpha d theta. Does that remind you anything similar from kinematics part? Haojin, do you remember something like this for linear displacement? What was the equation similar to this?
Yeah.
What was it? For velocity.
ADS equal VdV.
Exactly. You see, anything you had A equals dv dt or d2s dt squared, right? Now you have alpha d omega dt, d2 theta dt squared. You had vdv equals a ds. Now you have omega d omega alpha d theta. So technically, there's like an analogy between the three parameters or three pairs of parameter, S versus theta, V versus omega, and A versus alpha. And we're going to have similar things as we move to the kinetic parts. Okay. So similar to what you had for linear velocity SVA T, you're going to get this. So if you have an initial omega and a constant angular acceleration, your omega is going to be omega 0 alpha constant times t. Practically, if you integrate, just hold on a second. If you integrate this over time, you're going to get this. And if you integrate it twice over time, you're going to get this. And omega d omega equals alpha d theta. If you integrate that, you're going to get this. Looks familiar, right? We had exact equations for V, S, and alpha. And remember, these are all for constant angular velocity. AC is, if it's not constant, you have to integrate it, whatever the function is. So, as I said, there's an analogy between linear motion and angular motion. Technically, you add the word angular. So position is S, angular position is theta. Displacement is delta S, angular displacement delta theta, or ds d theta, same. Velocity V, angular velocity omega. Acceleration A, angular acceleration alpha. So you don't have to memorize this equation. If you remember those for S, V, and A, you can replace these parameters and get the same equations. So all calculations for angular motion is similar to what you had at the beginning of chapter 12, like rectilinear motion for S, V, and A. Any question? Okay. Now, when you want to do, let me get this word pure off here. So I just said it in a couple of slides back that angular position and displacements are not vector. And I'm going to explain you why. Imagine you have a sphere like this, and you have a point on this sphere. If I rotate this 90 degrees around axis Z, the way it shows, where does point go? Can you see that? If this rotates 90 degrees, it goes from here to here, right? Now, if I rotate it about X 90 degrees, where it goes? Goes from here 90 degrees all the way to the top. Now I'm going to replace or switch the displacement. I'm going to go with theta X first and then theta Z second. If this rotates about theta X 90 degrees, where does this point go? Yun, where the point goes? If this rotates about X 90 degrees, this sphere rotates about X 90 degrees. Okay, Jake, you tell me. I'm going to go with a Jake Z. If this rotates about 90 degrees, about X 90 degrees, where this point goes?
Doesn't it just stay right where it is?
It's going to be exactly, it's going to be where it is. So technically, if you rotate 90 degrees about x first, this is going to stay there. And then if you rotate 90 degrees about z, it's going to go here. Now, theta z plus theta x, here you have theta x plus theta z. Is the result the same? No. So they violate the commutative law of addition, right? Vectors, you can switch A and B and C. If you have even more than two vectors, you add them, doesn't matter the order, and they're going to be the same. Angular displacement are not the same. Okay? Therefore, large angular displacements and large angular positions are not vectors. Now, let's see what happens if these displacements are very small. I made this a little bigger, so we're going to go very small angular displacement. First, I'm going to rotate, but I want you guys to pay attention because this is a small, I want to just look at the slide for now, for like a minute. It's here. I'm going to rotate about z a tiny bit of dz, right? This is d theta z. So theta z rotates slightly about this. And then I'm going to rotate about y, small angle, d theta y. I'm going to keep this point and remove the rest. Now I'm going to go about delta y first. And then I'm going to go about delta z second. Do you see the summation is the same? Right? So technically, what you could not do for large displacement, you can do for a small displacement, which means we can consider small angular displacements as vector because they support switching A and B and C and all parameters together. Remember, what I show you here is not even differential. This could be like 10 degrees. Differential means close to 0, and that's more perfect, right? So if a small displacement, angular displacement could be vector, then d theta dt, which gives you omega, that also could be vector. And if omega is vector, the omega dt is also vector. Remember, we create a convention that omega and alpha and d theta are vectors, so it helps us to solve more advanced problems, right? Now, every vector has two parameters to know it. First one is the magnitude. The second one is the direction. The magnitude of this, you can get how much theta changes over time. You can get the function. How about the direction? For the direction, because this is a convention, it's not like a real vector. We define them to be vectors. We use the right-hand rule. Do you guys know what right-hand rule is? I want you guys to just look at the screen. If you can see me, this is my right hand, right? Right hand says if the four fingers show the direction of rotation, the thumb shows the vector. So technically, if something rotates like this, omega is going to be perpendicular to that plane of rotation. And the same for alpha. So practically, if you use the right-hand rule, the four fingers go through the direction of rotation, d theta, omega, or alpha, and the thumb shows the vector. So technically, omega, alpha, and d theta are perpendicular to the plane of motion because plane of motion is like this. The thumb goes perpendicular to this. Does that make sense? We define it this way. And we use this definition later. You see, it makes life easier. Any question? By the way, I'm going to ask you again, is the pace of my speaking good? Is the accent, do you understand what I'm saying, right? Anytime I say something, you don't get it, or maybe I pronounce it wrong, feel free to correct me or ask again, okay? I don't feel offended. I can learn something from you guys. So feel free to correct me if I say something wrong. But if I go a little quickly, just ask me to go slower. If you need a pause to write down the stuff, let me know. I give you a pause to write down so you don't want to fall behind. Okay, so up to here, we defined omega alpha as vectors. Now see how, I think I'm going to have to delete a lot of these pure words here. Okay. So to analyze the rotation about a fixed axis, just rotation only motion, let's consider this rigid body, right? The same like doner kebab or a shawarma thing. Point P rotates about a fixed point, which means it's going to move on a circular path. Is this correct? And suppose that your reference point is somewhere, it doesn't have to be at the center of this circle, because you go another point, you're going to have another circle. So if I have my reference point somewhere, it could be this point, it could be that point. O prime is the reference point for any position vector. So O prime shows from O prime to P is the position vector RP. The angle between this RP and the rotation axis is phi, the Greek letter phi. And P moves on a circular path, right? What you remember from kinematics, velocity is always tangent to the path of motion. So velocity has to be tangent to this circle at this moment, right? So this is how we define the position from the center of the circle. The position vector is R. From a base reference O prime, the position vector is RP, and we want to get the velocity in terms of RP. But you guys know that if P moves on a fixed radius, how much is the velocity? It's going to be R theta dot. Let me go to the tablet and remind you the polar coordinate system for velocity and see why we get this thing. So remember, when we had a path of motion, a reference line, and the position of the particle P as RP, and this was UR, this was U theta. This is just reminding you the kinematic parts. And the velocity as a vector was R dot UR plus R theta dot U theta, right? You remember this? You better remember, because on Monday you have a midterm and these things come, right? Now, for a circular motion, like the case we have rigid body, R is constant, right? which means this guy will be 0. So your velocity is simply, the magnitude of velocity is r theta dot. And we know that if this is theta, the way we defined d theta dt, which is theta dot, now that we have rigid body, we can consider the change of theta as the change of orientation of a rigid body. We can also call this as omega, right? That's how we define omega, d theta dt. So technically you can write this as r omega. And that's how, if this is the donor kebab things, you have this r, you have the point P, and it's going to have a velocity tangent, right? That VP comes from here. So does that clarify things? That is how we get this equation. Okay. So for this P, the velocity is r times omega. However, I'd like to have this in terms of rp, right? Because r could be anything. My reference point is O prime. I mean, you could use O as your reference point and change it for any point going up and down. Or you can say, you know what, I'm going to fix this O as O prime and do it. That's fine. How I can find R in terms of RP? If you look at from the side, if this is the circle, this is the center of the axis of rotation, this is your R, the angle phi, RP. If you look at this triangle, obviously your R is RP sine phi. And I'm going to substitute this here. So your VP is going to be RP omega sine phi. Looks good. So I found the velocity of P in terms of the angular velocity of the object or the rigid body and its position vector from my base reference point. Now, remember, we define omega as a vector which is perpendicular to the plane. Technically, omega is parallel to the axis of rotation, right? So omega is a vector here. RP is a vector here. And literally, sine phi is the angle between two vectors. Because if this is RP and omega is in this direction, then phi is the angle between RP and omega. Now, two vectors multiply the magnitude and then multiplied by the sine of the angle between them. Does that remind you anything from your math stuff? Nothing? Heisi, does that remind you anything? I think you have had this in physics 1. You probably have had it in physics 2 when you talk about electromagnetic. You guys passed physics 2, right? I don't know what the number is, the course number. We was used to call it physics 1, physics 2. So you had electromagnetic stuff. So you have seen this expression before. And that should remind you something. Heisi, do you remember what this represents? No? Okay, that's fine. That's fine. If you have two vectors, you multiply the magnitude. Remember, the result of this operation is also a vector. So let me make it simple for you guys. Two vectors times sine, the magnitude times sine gives you the third vector. This is the definition of cross product of the two vectors. So technically, you can write velocity as cross product of omega and position vector. And remember, the cross product is perpendicular to both vectors, which means if this is the plane of RP and omega, VP is going to be perpendicular to this. That makes a tangent to the circle. So it satisfies the tangent condition. It gives you the actual magnitude, and it makes life easier. Now you see why we define omega as a vector, so we can use it here like this. Any question? Now, I put my O prime here. I could also use O as reference point and say, you know what, this is my position vector. I don't care about that point. I'm just analyzing point P. The center of that circle is a good point to use it. If that's the case, fine. This is your position vector. Velocity is going to be dr dt, and then the result is going to be omega cross r. Both of them are valid. Because here, r and omega are perpendicular, the sine of the angle between them is 90 degrees, and sine 90 degrees is 1, so that's still okay. Still, you get the magnitude of velocity as r omega. Any question? Did the derivation confuse you? We defined omega as a vector, and we were able to use cross product of the vectors to get the velocity of the point based on position vector, omega vector, and the result, the velocity is also vector. Right? Easy like piece of cake, almost. I always joke that dynamics is like a piece of cake, but you have some jalapeno on the top, so it's kind of burns when you enjoy it. That's my feeling of dynamics. Jalapeno cake. I don't know if it exists, but if there was one, we could call it dynamics. Until you get the next course, which is more difficult, then you change the name to that course. Now we got the velocity. You want to find acceleration. Let me go back to the slide, to the tablet, and derive acceleration here, step by step. So we found velocity as omega cross RP. By the way, in my writings, I use this kind of a star with a circle for cross product, so we don't mix it with X, okay? You can use the same because sometimes you have X and it may become confusing. So you have omega as a vector and RP. Now, acceleration of P is dVP dt. That is general. You don't alter the most general equations. You can use it anytime. And if that's the case, you're going to get ddt of omega cross RP. Now, the cross product, you can still treat this like a regular product. So you have a product of two parameters, both of them variable. When you take the time derivative, you are going to use AP is ddt of omega cross RP plus omega cross drp dt, right? I just expanded the differentiation. Now, what is the omega dt? We just defined it, right? What is the omega dt? Come on, guys. Say something.
Alpha.
It's alpha, exactly. It's alpha, then cross RP plus omega cross. What is the RP dt?
Is that omega?
Isn't this VP drp dt? Which means technically this is the RP dt, right? It's velocity. Just like that. So technically, your acceleration is going to have two terms, alpha cross RP, omega cross omega. Remember, you cannot switch the brackets between omegas because remember, omega cross omega is how much? Any vector cross itself, what is the result? It's going to be omega, the magnitude, times omega, the magnitude, times the sine of the angle between them. What is the sine of the angle between omega and omega? It's the same as 0, right? So this gives you 0. So this is going to be 0, which means you cannot switch the brackets for cross product. And that's how you get. But if you expand omega cross omega, and I sometimes do this in the class showing my hands and right hand rule. If you expand this, you can get minus omega square RP. These are equivalent. So AP we can use either of these two equations. Of course, the black one is easier because you get rid of some of the omegas. That's how you find the acceleration of P. Now, if you want to use the radius of that circle, you can write AP is alpha cross R minus omega square R. This R has to be vector. Okay? And that is how you calculate acceleration of a rotating point on a rigid body. So this is practically the same thing. You get the cross product in the derivative, separate them. This becomes alpha, this becomes omega cross omega RP. Technically, this is your tangential acceleration. This is your normal acceleration. Remember, you have rotation of a point on a circular path, so you can divide your acceleration into normal and tangential. So technically, if this is your rigid body rotating about fixed point, R omega squared, the magnitude, goes toward the center, and R alpha is tangent to the path. That's how you can analyze them. And if you simplify it, as I said, you can simplify this to get this form. You can use any of them. You can use RP, you can use the radius, you can use omega cross omega, or omega squared times R. Remember this, the sign here is negative because R goes this way and normal acceleration is toward the center opposite direction. Any question? Okay, good. So that's how you analyze rotation of a rigid body. You can pick any point on the rigid body, get the velocity from this expression and acceleration from this or this expression. Okay. We're going to do a couple of examples, but I'm going to give you a few minutes of break, maybe 5 minutes. It's 10:57. Come back at 11:02. So I want this little settle down because some of the concepts would have been or could be little, new. I just want to give you, a few minutes to settle this in your mind. We'll be back in 5 minutes. I'm going to keep recording, share the screen again. So we developed those equations for velocity acceleration. Remember, all of those equations are in vector form because velocity and accelerations are vector. Now we're going to try that with a simple example here. You have this L-shaped rigid body, right? It rotates clockwise, so it shows the omega. And it says the angular velocity decreases at the rate of 4 radian per second, which means if omega is this way, alpha has to be negative of that opposite way. We want vector expression for velocity acceleration when velocity is 2, because there's alpha velocity changes. At the moment that velocity is 2, we want to find the velocity and acceleration of point A. So to do that, I'm going to give you 30 seconds to draw this, and I do it on my tablet. So you need to find the position vector for A. And then position or angular velocity and angular acceleration for A. And that's how you solve this problem. So the coordinate system XY is given. Let me share the screen here. This is the thing, right? So the X of A is 0.4 meter. This is 0.4 meter. This is 0.3 meter. This is 0.8. This is your omega. And this is your alpha. Omega is 2 radian per second. alpha with the direction I show is 4 radian per second squared. Remember, it says decreasing, but I already applied that negative, and we really don't know as a vector if omega is negative or alpha. We're going to practice that and see how it goes. Any question about the physics of the problem? Looks okay, right? So if we solve this, the first thing is to find RA as a vector. This is X of A, and this is Y of A. Both of them are positive. So technically, RA is 0.4 I plus 0.3 J, right? As a vector, if you use your right-hand rule, definitely omega is in Z direction, right? Omega and alpha are in the direction of Z. Now, which one is positive? I want you guys to use your right-hand rule. Remember, the way that we have X and Y set, Z comes out of plane toward us, right? In XYZ. Now, you guys tell me if I write omega as a vector, is it 2 times K or minus 2 times K? And when you get this, alpha is the opposite of that. I want you all to use your right-hand rule to see if the direction of omega is in positive K or negative K. And give me what you find. Like, hi Z, is omega positive or negative?
I think omega is negative.
Negative, because if you get your fingers toward the omega, your thumb goes toward the plane or toward your paper, but positive K coming out of the paper. So this will be minus 2K. And because omega alpha, if you go alpha, alpha goes toward outside the paper, that's going to be positive. So the rest is simply doing the cross product. And I am expecting some of you may have forgotten how to do the cross product. So VA is going to be omega cross RA. If I substitute that, minus 2K cross 0.4I plus 0.3J. Do you guys remember what happens for the cross product of IK, IJ, JK? Because if I expand this, and we're not going to do this in too much detail, I'm going to do it just for this problem so you remember. Technically, you're going to get minus 2 times 0.4, the first one. Then you're going to get K cross I. Then for the second one, you're going to get plus minus 2 times 0.3 K cross J. What is K cross I? Do you remember? These are unit vectors, so the result is going to be a vector which has a unit length and is going to be perpendicular to both of them. It's either J or minus J. I give you a reminder. So K cross I, you guys remember? Obviously you don't. Okay. There was a way to do this. If you do I, J, and K, and if you go clockwise, look at here for a second, please. Do not write it. I cross K gives you J. J cross K gives you I, and K cross I gives you J. If you go clockwise, they're going to be positive. If you go counterclockwise, like I cross J is going to be minus I, sorry, I cross K is going to be minus J. K cross J is going to be minus I, and J cross I is going to be minus K. Right? Now, here we have K cross I. K cross I is clockwise, so it's going to be positive. 2 points is going to be minus 0.8. K cross I, J. K cross J goes in a negative route, so it's going to give you negative I. Okay? So if you simplify it, it's going to be 0.6I minus 0.8J. I'm going to write it here if you want to memorize it or write it somewhere. I'm going to write it here just for you guys to have it with the purple. So I cross J gives you K, J cross I minus K. J cross K gives you I, K cross J minus I. Then K cross I gives you J, I cross K minus J. You either memorize this or counterclockwise positive, sorry, clockwise positive, counterclockwise negative. When you go like I, J, K, this is positive, this is negative. That's how you remember. I think for me, this is easier. Technically, I wrote this from here. Okay. Now, we're going to go to acceleration. For acceleration of A is going to be alpha plus RA minus omega square RA. Remember, this is omega square is just a number, right? The vector part goes from here. And if I do that, alpha was 4K plus RA 0.4I plus 0.3J. And then minus omega square, which was 2 square 0.4I plus 0.3J. I'm going to do this one again. Please do not write and look at here for a second. You know what? I'm going to give you a minute to finish this part. Then you look when I do the IJK, so you can follow. Is everybody done writing this? Okay, so I'm gonna put the numbers first. So we're gonna get 4 times 0.4. Let's just put the number. 4 times 0.4 is gonna be 1.6. K cross I is gonna give you J. 4 times 0.3, 1.2. K cross J gives you minus I. Here, this is 4. You're going to get minus 4 times I, sorry, times 0.4. 1.6 I minus 1.2 J. This is just a regular multiplication. And if you simplify that, you're going to get I minus 1.6 minus 1.2, 2.8. And this is ugly. This guy and this guy minus 2.8 I. Then you go this guy and this guy plus 0.4 J. This is overall acceleration. Remember, this is the tangential acceleration. This is the normal acceleration. Any question? Okay. So just a reminder, if this is your position vector, let me get rid of these things first. If this is your position vector, RA, then the normal acceleration is going to be in this direction. Right? This is going to be your AN, which is equal to R omega squared. And the tangential acceleration is going to be perpendicular to this. Right? And its magnitude will be R alpha. These are the magnitude already. We have done already the cross product thing. So this is just the magnitude. Later, you can just write R omega, R alpha. Remember, this is always toward the center. And that's why you have this negative sign here. Right? Which means this is in direction of R, but going backward with the negative. Any question? Okay, let's go back to the slides. This is another example. You have this windmill You have 2 points on the windmill. One is 10 feet away from the axis of rotation. One is 20 feet away. It says the blades originally are at rest and begin to rotate. Alpha C is constant, and as you see is in this direction, half radian per second squared. We want to find the magnitude of the velocity and acceleration after 4 seconds. So to do this, you obviously need to consider the time relation between alpha and omega and theta and everything. Remember, anytime you do omega and alpha, the angle has to be in radian. When we measure the angles 30 degree, 45 degree, you go with degree, that's okay. But for those calculations, you have to consider radian. So the information we have, alpha C is 0.5 radian per square second. Time is 4 seconds. Omega 0, initial omega is 0. Then RB is 10 feet and RA is 20 feet. Okay. So to solve this, omega, first of all, if this is Z, let's say I have my X and Y like this. So this Z, your alpha, is positive 0.5 K. Or I can go with normal tangential acceleration, right? Like AB normal is RB omega squared, and AB tangential is RB alpha. And same for AA normal, RA omega squared, AA tangential, RA alpha. These are just the magnitude. Obviously, the tangential acceleration, if you rotate like this, is going to be AT or ABT, and the normal will be like that. And this is obviously path of motion, right? So the problem gives us t equals 4, alpha constant 0.5. So you find, if I want to find omega at any time, which is this time, omega at t equals 4, it's going to be omega 0 plus alpha constant t. Remember, this equation is only for constant alpha. So then omega is going to be 0.5 times 4 2 radian per second. So VB is going to be RB omega, which is going to be 10 times 2, 20 feet per second. VA, RA omega, 20 times 2, 40 feet per second, just like that. You don't have to do cross product because we just look for the magnitude. Okay? Any question? And of course, as I said, if B rotates like this and A rotates like that, velocity of B is going to be tangent in this direction and for that guy in that direction. These are supposed to be tangent. I know it's like a 3D, it's hard to draw it, but you get the idea. For acceleration, AB normal is going to be omega square RB, which means 2 square times 10, 40 feet per square second. AN omega square RA, 80 feet per second square. AB tangential is going to be alpha RB 0.5 times 10, 5 feet per square second. And AA tangential per second. Okay. It's like we are analyzing the motion of A and B in normal tangential coordinate system or polar coordinate system rotating about a fixed circle with a constant radius. We can get it like that. Okay. Any question? Okay, now the problem asks, I guess, for the magnitude of velocity and acceleration. We found the magnitude of velocity. This was VB, this was VA. For the magnitude of acceleration, however, we have to consider normal components and tangential components together. So AB is going to be a square root of ABN square plus ABT square, which is going to be 40 square plus 5 square. It's going to be 40.311 feet per second square. And for AA, you have 80 square, this guy, and this guy together. Which is 80.622 feet per square second. Any question? Okay. So these were two examples of how you analyze rotation about fixed axis. There is one more example. I'm going to do this later, maybe, or maybe not, because this is similar. I'm going to explain it to you. You know what? I'm going to start this example and leave it to you to finish as a bonus problem. Okay? Do you like that? So in this example, as you see, you have a set of pulleys and belt. It says when T is 0, at the beginning, it doesn't start from rest. Pulley A has an electromotor that rotates it with the 5 radian per second. All the radii are given here, 4.5, 5, 3, and 4. And it says the pulley has a constant angular acceleration of 2 radian per second. You want to see how much is the angular velocity of B after B rotates 6 revolutions. So some information is given on A, some information is given on C. And it says C and D are rigidly connected, so they rotate together. Okay? So this is like slightly different example. You have to relate the motion of pulley A to C and C to D and D to B. So that's how we analyze this. And because it says the omega is counterclockwise, as you can see, the problem says the angular acceleration is also counterclockwise, so it's technically the same direction. Now let's see how we do this. So the problem wants to find when B rotates 6 revolutions. So delta theta B is going to be 6 times 2 pi, right? Because each revolution is 2 pi, 6 times 2 pi. I'm going to write down the magnitude for the radius of each of the things. So RA 4.5 inch, RB 4 inch, RC 5 inch, and RD 3". Now, we need to relate the omega of pulley A to pulley C. Do you guys remember how to do that? When you have two pulleys, excuse me, you have two pulleys or two gears or two sprockets that rotate together. The condition is this. This belt here that goes around, does it compress or stretch the belt? Does it change its shape as this system works? Come on, guys, give me yes or no.
No,
No, in a continuous, you may say, you know what, it stretches a little bit, but is in a continuous system, after it starts moving, that little stretch again we neglect, which means whatever the velocity of this point, let's say point M is, as this goes here, M prime is the same velocity, right? So velocity of M, I can write RA omega A, right? Because M is on the perimeter of pulley A and rotates like that. Velocity of M prime, again, M prime is on the perimeter of pulley B, pulley C, sorry. RC omega C. And because the pulley doesn't compress or stretch, we know that Vm is same as Vm prime, which means RA omega A is RC omega C, which means omega C over omega A is RA over RC. That is how you change the ratio of angular velocities, right? Then what happens between C and D? Problem says C and D are rigidly connected together. They're technically on the same shaft, rotate together, right? If they rotate together, therefore, omega C is same as omega D. Right? Because C and D are rigidly connected to the same shaft or to each other. Okay? Then what happens between D and B? Again, you have a pulley similar, I think we had here, we're going to have here, right? I'm not going to put M prime and anything anymore. I'm going to reproduce this equation between D and B. So omega B over omega D is going to be RD over RB. You just flip the radii versus omegas, right? So if that's the case, I can write omega C is RA, RC, omega A, which is same as omega D. And then omega B is RD, RB, omega D. I'm going to substitute this guy here. So I related omega B to omega A using the radius of each of them. If you put the values, RD was how much? 3 divided by 4. And then here you have 4.5 divided by 5, right? .675 omega A, right? At any time. If you take the derivative of this, you may realize that also alpha B is 0.675 alpha A. And if you integrate that, you're going to get delta theta B is 0.675 delta theta A. So that is how you can relate. Now, delta theta B is given. I can either get this guy and continue, or because omega alpha A is given, I can go backward. Okay? So I want you guys to complete this. I did the derivation of how you can relate omegas and alphas and delta thetas. Then you go and solve the problem. I'm going to create a link. The due time for that is tonight. Please do not look at the solution manuals or any resources. Try to figure this out. If you are not too hungry to go for lunch, I recommend you to spend 10 minutes, 15 minutes right now after this, okay? So you can do it. Everything is fresh in your mind. Find the solution and submit it. Any question? Did you guys enjoy the lecture? Did you learn something today, right? Hopefully. Okay, I'm going to stop the lecture today. Remember, Monday, we have a midterm. It will be chapter 12 to 15. And you have 75 minutes for the exam, like regular lecture time, okay? Like regular semesters. After that, we continue with this chapter, okay? Please make sure.
How many questions are going to be on the exam?
I haven't designed it. 3 or 4, not more than that. Because usually each problem takes 20 to 25 minutes to solve. Sometimes a problem is shorter, take maybe 10, 15. Then I may add another shorter problem, but that's usually what it is. It will cover the entire content of particles. Of course, you have access to your notes, to everything you want. Sometimes I'm lazy to solve quadratic equation. I Google their websites that do that for you. If you can, I mean, in a regular exam, you can do it, but now you can't. So if you want to do it that way, save like 1 minute, I'm fine with that because you are in front of your computer. But other than these things, getting through other resources or talking to each other, if I find similar solutions, I may have to act one way or another. So please make sure, because some of you may be, I don't know, roommates or friends sitting in the same room. It doesn't happen as frequently. It's happened in the past that 3 students, they're friends, roommates, they're sitting in the same room doing the exam. They did everything independently. A part of a problem, they kind of tempted, hey, for example, Jack, how you do this? And I did that and blah, blah. And interestingly, that part was wrong. So each of them could do it themselves and get better result. But anyway, please do not do any of that. I don't want to get into the point that I will, you know, start disciplinary action, because I told you that's not the type of person I am. And that's not the type of person I want you guys to be. So make sure you do it all yourself. You're going to have 75 minutes for the exam. 10 minutes to submit it, because you may have multiple pages to scan. Please scan them using a scanner. If it's not good, I may have to ask you to submit it again. And as I said, that is not very good for people of your situation, that you submit something and it's not readable. If you use pencils, make sure they're sharp, because sometimes you write it very, you know, thin, and when you scan it, and some papers are yellowish. So I have hard time seeing it, okay? So that's it. We are 5 minutes over time, and I will see you guys on Monday. Make sure you get into the lecture session, maybe 5 minutes early, settle yourself, put your, you know, get yourself ready. The format is going to be the same. The link for the problems will be available right at 10 o'clock. And the submission link, of course, same time. You get 5 extra minutes after 75 plus 5 to submit it with penalties. After that, I will close the submission link. Make sure you use your time wisely. Don't wait till last minute, because if you cannot submit it, remember, if you don't finish a problem, you may lose 5-10 points. If you cannot submit it, you get 0, right? So don't risk till push it to the last minute to use 85 minutes for solution. But I leave the rest to you. If you have any question and need help, please let me know. As I said, I will post the solutions for chapter 15 on Sunday morning, and I'm going to create a link for this bonus problem to submit it by end of tonight. Any question or comment? Okay, thank you very much, and see you guys on Monday. Goodbye, and have a good weekend.